Hello, and welcome to another video in this series as we learn the basics of Prolog together. We're actually coming towards the end of the course, and in this final section, in the last few videos, we've been looking at metaprogramming and writing Prolog to run a Prolog program. And the aim of that is to control or adjust or extend how a Prolog program is run. We started with a very minimal, probably the smallest meta interpreter, and then over the last two videos we've extended it a little bit, just to see how we would grow the capabilities of a meta interpreter. And what we've seen is a fairly standard pattern, which we'll remind ourselves of in a minute. Today's video is really about quite a challenging task, and that is meta interpreting the cut. If you've had a little think about it, you can imagine, well, we know the cut is a little bit different to most Prolog. It behaves differently, and meta interpreting it will require a little bit of extra care. So that's what we'll do today. But before we dive in, let's sort of refresh ourselves. So on the screen you can see the meta interpreter that we developed last time, and we're just going to look at the key features of it, because when we extend the meta interpreter, we do it by extending a standard pattern. So over here we've got the main part of our meta interpreter, which takes a query and then proceeds to prove it by finding a relevant rule in the database and then trying to prove the body. In our example, we are kind of printing out an explanation, as it were, but this is the heart of the engine, as it were. It's taking a query, seeing if it can find a relevant rule in the database, and then using the body of that rule, proving it. And that's what Prolog would do itself anyway. Our extension here is simply to write out an explanation. Vanilla Prolog wouldn't do that. In the final video next time, we'll see other things we can use a meta interpreter to change how Prolog is run, but that's next time. We extended last time our meta interpreter to cope with rules that had a body of more than one property, more than one goal. So that was useful because lots of our useful Prolog programs don't just consist of a head and then a body of just one property, and that used recursion to unpack a sequence of Prolog in the body. So you've got a head, you've got a query. If the body is a sequence of goals, then proving that matches this construct, A, B, where that becomes the first goal and B is the remaining sequence of goals. So we did that last time. And then we have built-ins. So this deals with properties. And then we've got built-ins. So true is the body of a fact, and we needed a way of handling that, and it's just true. And we put a cut in so that if this was matched and succeeded, our meta interpreter wouldn't backtrack and then match this again if this has already matched, because this proving true matches this rule, specific rule, but it also matches this general rule. In fact, proving anything will match this, so we have a cut everywhere here. We have a built-in. Last time we looked at the unification symbol equals, and that was easier to implement after we thought about it. And you might say, well, and this is easily extended, this pattern. So if you have another built-in like A is B, well, it's the same pattern. We have a cut to prevent backtracking so that we don't match this again, and then we prove this by execute it as well, simply by running that itself. So it sounds like a tautology, but it's to prove this, you run this. So this is true, or this is true. The proving of this is true if this is true, and the same applies for other built-ins. I can't think of one example right now, but I can't think of anything right now. But if there were other built-ins, you follow this pattern. But the cut doesn't follow this, and that's why we have to kind of move away from this pattern a little bit. So just want to pause there and say this is the general pattern for a lot of the meta interpreters that you might write. You have something that is the core engine. You might have something that matches different kinds of rules. Here we're matching rules that have multiple goals in the body. That usually covers most of the Prolog programs we're interested in. And then you've got any specific built-ins that would go there. That's the general pattern, but the cut doesn't suit that. Let's see why. So if I've got just a rule, I don't know, happy x, which is true if 1x is true, and there's a cut, and then there's another property there. Just speaking in generalities here, if we were meta-interpreting this, we try to prove this, which would lead us to the body of the rule, and then using this recursion, we chop off the head of this sequence and prove each goal. So we prove this one first, and that might be easy because it might be a fact, or it might lead deductively onto other goals, and that's fine. Our meta interpreter can cope with that, so that's fine. Then we have a cut, and you might say, okay, cut always succeeds, so it's always true, but it does have some side effects. So how do we meta interpret that? Let's come back to that. Let's imagine we have done that and it succeeds, and then we meta interpret this, and that's fine as well. But this thing, it succeeds, so you might say our kind of matching us kind of special kind of rules for the built-ins might be something like to prove the cut, we follow the standard pattern here, where we have a cut here to prevent backtracking. So we have a cut there, and then we implement here the thing that we are trying to prove. So you might say the cut again, that would follow the pattern. But the cut does two things. One of the things a cut does is be true, and the other thing it does is prevent backtracking. This succeeds it succeeds by being true. In fact, you don't need to, but I'm just following the pattern. So it implements this side effect or effect of the cut, but it doesn't do this, because this prevents backtracking in this meta interpreter code. It doesn't prevent backtracking in the code being simulated in emulated. It doesn't prevent backtracking here in this rule. Do you see? So backtracking happens in the line of code where the cut appears, but we want it to happen in the line of code of the program that we are simulating, emulating, interpreting here. So that's a challenge. So let's think a little bit more about this. What in general, let's zoom out and think, how would we achieve something like that? We seem to be asking for an effect, a side effect that's wider than any of these kind of meta interpreter rules. Let's draw another picture. Let's say we have a Prolog program which we want to emulate, simulate, run through our meta interpreter, and it's got goal 1, goal, if I can spell, 1, it's got a cut, and it's got goal 2, so very similar to what we've just spoken about. Our meta interpreter can try to prove H, and to do that it will find the body of this rule. It will then try to prove this. Job done. Let's come back to the cut. It'll try and prove this. That's easily done by our current meta interpreter. But this thing, if we were looking at this program in isolation, we want this cut to prevent backtracking back along here. And if there were, for example, multiple rules, H, 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 and there's a cut here, we don't want it to try any of the other ones. So the effect of this cut affects the entirety of the evaluation of H. Over here in the meta interpreter code, we somehow need to achieve that wider scope of effect, and we can't do that simply by writing prove cut is a cut and then a cut, because this prevents backtracking here, and once that's done we'll move on to goal 2 and there will be nothing that prevents backtracking. So in some way we want some way of communicating back out to when we first consider the rule H, some kind of message to be sent, some kind of signal that goes out from here, from when we find the cut, all the way back out to H to say, right, found the cut, stop, don't do any more once you've succeeded after the cut. So this kind of message mechanism is something we need. That's quite a kind of a big leap, I guess, for if this is the first time you've kind of thought about it. I say the blog itself talks about this in slower, more deliberate words. So do have a look at the blog, because the words I use there are more carefully chosen. On this video I'm just talking to you off the top of my head, trying to kind of share with you the kind of thinking. But the important point here is that the cut is sufficiently different because its impact is wider than just where the cut appears. It affects the entire line of code in which the cut appears, and can affect multiple lines of code if they relate to the same property that we've talked about here. So we need some way for the meta interpreter to find a cut and then signal back out to to the kind of zoom out and say, okay, we were looking at proving H, let's stop and not continue once that's once we've found the cut and kind of executed it or simulated its execution. So if you want to pause there and just digest that, please do. If you want to read the blog, this is a good point to do it. What I'm going to do now is talk about this mechanism for sending a message, and that's called throwing and catching exceptions. It's a bit of a hack, because throwing and catching exceptions are really meant for exceptional circumstances, dealing with errors, not really in the routine running of programs. So it's a slight abuse of a mechanism that exists in many languages, including Prolog. So if you know about exceptions, throwing them and catching them, fine. and you can kind of zoom through that bit. But if you've not come across them before, I'm going to explain them. Just before I move on, this is a picture on the blog just showing that this kind of rule, this H, property H, that needs 3 things. It's got a goal 1 and a goal 2 and a cut in between. And the meta interpreter, to prove H, will prove goal 1, will prove the cut in some way, and then prove goal 2. But when it does the cut, it needs to send a signal back somehow to say, all right, don't backtrack, don't try any other lines of code which have H as the head. So this is visually showing what's happening there. So an exception, you very likely have come across them, because on our journey in coding, learning to code Prolog, we will inevitably have made mistakes or written code that kind of runs into problems. One of them is where we write code that seems to go into an endless loop and then runs out of memory and crashes. So let's try and induce that ourselves. Let's write a rule called bad, and you can see bad x is true if bad of bad x is true, and you can see it's very circular, almost doubly circular, and it's deliberately written to enter into a loop. To prove bad x, you need to prove that bad of bad x is true, and then you can see how, as Prolog tries to prove that, it kind of grows the memory used to keep track of where it is in trying to prove this very circular argument, and then eventually runs out of memory. So let's try and prove that. And this we're doing this intentionally to cause an error. Might take a few seconds. So it's still running, and there you go. It's run out of memory. So the online version of Prolog has only 2.2 gig allocated to the stack, and your own one might take longer because it might have more memory to first exhaust. But this is an error message, and what happens in Prolog is that when something goes wrong, an exception is raised. An exception is almost like a higher priority message than normal Prolog running. So let's draw a picture. So imagine this is normal Prolog running along, doing its thing, and then when something bad happens, a higher priority message is sent. So Prolog is paused, a higher priority message is run, and that might be that's called throwing an exception. And then an exception is thrown, then something has to handle it. There's always 2 parts to it: throw and catch. So Prolog, when something goes wrong, throws an exception, and actually Prolog itself catches it and prints out an error message, and then aborts the execution of the normal Prolog program. And you can see how this has to be a higher priority because it needs to take precedence over whatever bad things that the Prolog program itself was doing. Now there's a whole list of standard categories for different types of exception. There might be a memory one, there might be something to do with disk space or something else. There's a whole list of, you can imagine there's a whole category of bad things that are happening and that could cause an exception to be thrown. Now the reason this is exposed to programmers, not just in Prolog but many other languages, is that sometimes you expect certain things to go wrong and you want to handle them in your own way. So you might say, okay, I expect division by 0, and instead of the whole program crashing, I just want to catch it, do something and move on. So you might have done that in Java or C or something like that. I personally don't like programming through the lens of exceptions, because it suggests that your program isn't general enough and has to work through exceptions, but practically you kind of have to sometimes. So we are going to use this mechanism for throwing an exception and catching it at a broader scope. So we're going to throw it when we find a cut, and then we're going to catch it in the scope of the entire rule that we were interpreting. So the mental image to think about is we create a scope. So we might have Prolog code like this, lines of code, and then we have a scope and say around these lines of code we're going to listen for an exception and handle it if we want to, so that if there's an exception created by one of the lines in here, it's relevant to an entire scope, and then we can either fail the entire scope or succeed or do something with it. This will become more clear when you see it for real. Actually, before we can do that, we need to define our own exceptions, and we do that by name. Different programming languages have different approaches for generating custom exceptions. In Prolog it's actually very simple, so you simply say I'm going to give it a name or a label. So I'm going to throw an exception of type, and then you can give it a name like, I don't know, bad number, or negative if you didn't like negative numbers, or whatever, and then you can listen for them. And if you can listen for a specific type like bad number or bad weather or whatever, and then handle them. And you can be general as well. You can say I'm listening for any type. So that's kind of a broad theory. Let's see some of that in practice. So just to illustrate this idea of catching, so this is the code that could potentially create an error. In fact, we know this does. So what I do is I have a catch. So the construct is catch goal exception handler. So this is what tells Prolog that around this goal I'm going to listen out for an exception of this type, and then I'm going, if you catch it, if you find one, then run this handler. So again, very simple, the bare minimum of a system for throwing and catching exceptions. Now remember, this goal can actually entail a lot of code, so it doesn't have to be one property. It can be multiple properties, or it can be a whole section of code, because we can say goal means lots and lots of things deductively. Exception, give it a name as long as it doesn't clash with other ones, and the handler is a property that is executed, and again that can be very simple or as complex as we like, because that can refer to lots and lots of code, because it's a handler which is true if lots of other things are true. So just very quickly we'll just show the simplest use of catch. So catch, if we have a general variable to catch any exception, so that's Prolog kind of flavor there, and as a handler we'll just write it out. That's our handler. So if we run that, we should, when the error appears, when we run out of memory, we handle it by writing out what the error was. And you can see the writing now has written out in a more structured way. We don't have to fully understand all of this, but that's what writing the exception, and this is the contents of that exception. You see it's a resource error on the stack, some description about what the stack looked like. The stack is just the memory used for keeping track of where Prolog is in executing a program. There you go. If we wanted to just ignore it, we could just say true, and if we run that, the handler will do nothing with it, so we won't see any error message. this is printing out E because it's a variable. If I then said underscore E, as in I'm not interested, then that truly will silence the problem. So the best way to kind of talk about how we implement the cut in a meta interpreter is actually just to talk through an example of how it's done. And the reason for that is it's not actually obvious how you might construct it from first principles. I'm sure there are people who are talented enough to do that, but I think most people, normal people, wouldn't come up with the answer. It's a bit of a hack. it's a bit creative, but it works. And the best way I think in this case to understand it is to talk through how others more talented than myself have solved this problem. So let's look at this code. This is from very early on in our course. Very, very simple. Fruit apple, fruit orange, fruit banana. And it was when we first introduced the cut. So when we said fruit apple, is that true? And of course it's true. Same with fruit banana. Of course that's true. And then we said fruit orange. And of course that's true as well. But when we said what are the fruit with a variable, and after orange it stopped, and that's because the cut prevented backtracking. So first apple is found, then orange. That succeeds but prevents backtracking, so banana is not found. That's how we introduced the cut all the way back in an earlier video. So this is our program, our test program, and we are going to want our meta interpreter to be able to run this and handle the cut correctly. And if you look at the structure of our meta interpreter, it's the same almost as before. You can recognize the three the sections of it. So there's the last bit here which looks like the main engine. You can see clause. So to prove H, we look up H in the database, find the body, prove the body, but there's some other stuff here which we'll talk about. Proving true, we've seen that all the way back to our earliest meta interpreter. We've seen this construct A, B in brackets, which picks apart a sequence of Prolog goals, in the body. If there's multiple goals in the body, we did that last time, so that's familiar. And then we've got something here which is new, and it's allegedly going to implement the cut. We've got the cut here to prevent backtracking, and this one prevents this matching if this is matched. So just like what this does and just like what this does, and it's just like what if we had A equals B, we'd do the same. We'd have a cut, then A equals B, and implement it like that. I've left them out now just for keeping the code small. So that's there, and so that's the reason that cut is there, but this is new. We say true and then we throw an exception called cut exception. And you can see here that this matches the two properties of a cut. Number one, a cut always succeeds as true, so that's what that does. But it also prevents backtracking, which is what this does, and we'll see how. You might be thinking, what's this bracket and what's this semicolon? If you haven't come across that before, let me kind of explain. So just to explain what that semicolon thing does, you might remember in Prolog where we have something like a property is true, and we might just say it is true, or we might say it's true if one property is true and another property is true. That's an and, that comma, it's a conjunction if you remember. What if we wanted or, not and, or? So at this point you're either very puzzled, or you might say there's no problem at all. We simply have two lines. Happy X is true if 1 is true, the first property, and we have another line, happy X is true if the second property is true. and this has the effect of all, either this matches or this matches, because if this one fails, then it backtracks and tries the second one. So the effect is this: if this one works, then this is true. If this one works, then this is true. So that's one way of implementing OR, a disjunction. But there is a kind of a shortcut way of writing that, which is to say happy x, which is 1 semicolon 2. And you can put that in round brackets if you want, just to group it together. So that's what this does. It's just a shorthand for doing it this way with 2 lines. So it's this, and then if it's a new line, this. It's almost as if it's creating a new line. That's just a shorthand. So that's what this does. It says it creates the true condition so that the cut succeeds as true, but then it throws an exception. That's a message that's now sent, but where do we catch it? Well, before we answer that, let's remember we want to catch it at the scope of the rule, the head of the rule that we are interpreting. So H was what we call the head of the rule, and that's why we say catch outside the clause. So if we say catch here, that means we start listening for exceptions of type cut exception. So we run the goal that catch will scope, and that is search for the clause. If it's got a body, prove it. So that's at the level of the line. Let's think about this one here. That's this, that's the head and that's the body. So we'll find this and prove the body. If in the course of proving the body we've come across the cut, then we say it's true, backtrack, throw an exception. True means that it succeeds, and then whatever needs to happen after the cut happens. That's an important point as to why this is a disjunction. The flow needs to continue after the true, because there might be things after the cut on the same line, or that's right, yeah, after the cut there might be other things that need to happen, and those also need to be executed. So the true means, yep, that succeeds, and then we carry on. But we also backtrack, and then we throw an exception called cut exception. That's the label. Remember in our previous example we said bad number, I think it was, or unlucky number. So this is cut exception, and that's caught. That's what catch is listening for. It catches it, and the handling of that is to fail, and that is to fail this entire clause. So it fails at the whole level of that line, but only after whatever was executed and succeeded up to the point of the cut, and then afterwards, because there might have been items after. So if they succeeded and generated solutions, fine. Let's kind of write that as the other way if we were going to do it without the disjunction. Can you see there? So put it on its own there. So we to prove the cut, to emulate it, we say it's true, and then the flow will continue. But when we backtrack, because we can match it again, we throw a cut exception, which is caught at the level of the query that initially we started with, the head of a rule, which is the right scope, because that's the point at which we want to say, right, do not continue, and we do that with the fail. Again, if you want a pen and pencil and paper, I recommend that. Work through it with the blog. Let's test this now. So we know that fruit X should generate just the first two, apple, orange. Let's try and prove that. Prove. This is now in meta-interpreting fruit X. Let's run that. So it's saying that X equal apple is true, and it's printing out an explanation, which is what our code does. It's asking us that there might be more solutions, so let's carry on. Orange. It's not just true, but there's a cut, which is this rule here. And then it doesn't produce any more. And we can see that that cut there is what prevented Prolog from finding more solutions. So we appear to have successfully implemented the cut. Phew, that wasn't easy, I have to say. That was quite involved. But there are some limitations. I think the first thing to say is it's not great code because it's naming an exception, and if your code, if you're working on large code and other people are throwing exceptions in your code, it's a joint project or you're writing code and that's throwing exceptions, if you happen to get the names mixed up, clashing, then this thing breaks down. The second thing is around performance. So what we are trying to do here is run normal code, running a normal program, but we are abusing the exception mechanism, which is only meant to be used as an exception, and there's a performance hit to doing that. We didn't really see it here, but it's not exceptions weren't designed to be run repeatedly many times in the course of normal programming. They are exceptions, so there's a performance hit there. So just two things to watch out for. But I guess this is even if you're not going to implement the cut in a meta interpreter, what we've done here is learned about exceptions and throwing and catching them, and we've also stretched our brains to see if there was a way to get a meta interpreter simulating the effects of a cut by being quite creative with how we use the scope of the catch for an exception. Fantastic. This is already quite a long video, so I'll stop there. The final thing I'd say is just to kind of reassure you, what we've done today is particularly kind of exceptional. It's not basic Prolog. I just popped it in there because it was interesting, and it might stretch some of you who find Prolog generally kind of easy. It was an interesting challenge, but you're not really missing out if you don't know how to implement the cut in a meta interpreter. That's really not kind of basic common core knowledge. Next time we will revert to the mainstream, and it'll be the final video actually in this course, and we will see another use of the meta interpreter where we're not just printing out explanations, but we're changing the way Prolog searches for solutions in a way that benefits us. So that's quite a distinct and really good use case for meta interpreters. Fantastic. See you then. Bye.